Unlock the secrets of Roman engineering that textbooks often miss. We're not just looking at the structures, but the software behind them, the ingenious, iterative calculations, and sophisticated problem-solving techniques. Discover the empirical algorithms that allowed ancient builders to perfectly plan and execute projects on a scale that still boggles the modern mind. When we stand before the Colosseum or gaze at Roman aqueducts stretching across valleys, we typically marvel at the architectural triumph. But we're missing something profound. Behind every gravity-defying arch and perfectly graded water channel ran a sophisticated computational logic, a kind of software written not in code, but in systematic procedures, geometric formulas, and iterative testing. Today, we're decoding the lost algorithms that made Rome's engineering possible. Roman engineers operated with three essential instruments that functioned as their computational toolkit. The groma consisted of a vertical pole with a horizontal cross, fitted with plumb lines hanging from each arm. By sighting along these perfectly weighted lines, engineers could establish straight paths and right angles across miles of rough terrain, essential for laying out aqueduct routes or marking the Colosseum's foundation. Think of it as their most basic programming tool, executing fundamental operations with precision. The dioptra represented a more sophisticated device, featuring geared, rotating plates and precision screws that measured angles and levels. This allowed engineers to calculate consistent gradients over enormous distances, essentially performing trigonometric functions mechanically. And then there was the chorobates, Vitruvius's favorite. This 20-foot wooden leveling table, equipped with plumb lines and a water trough, verified measurements directly in excavated channels. It was their debugging tool, catching errors before they became catastrophic. These weren't just measuring devices. They were computational instruments that enabled complex calculations without calculus, without computers, without even efficient number systems. And the Romans wielded them with remarkable sophistication. Here's where Roman engineering reveals its true algorithmic nature. When planning an aqueduct, engineers didn't calculate the entire route theoretically and then build. Instead, they executed what modern programmers would recognize as an iterative algorithm. Survey a segment, calculate the required slope using empirical formulas, excavate the channel, verify with the chorobates. If the measurements revealed deviations, adjust and recalculate. Survey the next segment. Repeat. This trial and error methodology prioritized practical accuracy over theoretical perfection. And the results speak for themselves. Some Roman aqueducts maintained slopes as gentle as 1 in 4,800, dropping just 1 foot vertically for every 4,800 feet horizontally, across dozens of miles. That's not guesswork. That's systematic computation, executed through iterative refinement. The mathematical foundations underlying these techniques relied heavily on geometric principles. Roman engineers used the Pythagorean theorem to compute relationships between horizontal distance, vertical drop, and the actual channel length required across uneven terrain. But here's what made them brilliant. They didn't just apply abstract mathematics. They developed empirical ratios through observation, creating reusable formulas that functioned like code libraries. These ratios, refined through generations of engineering experience, could be applied across different projects, scaled up or down, while maintaining structural integrity. Their concrete technology itself represented a computational achievement. Engineers developed specific lime to pozzolana ratios, typically 1:2, 1:3, or 1:4, depending on the application, through systematic testing. Pozzolana, volcanic ash from regions near Mount Vesuvius, reacted with quicklime and water to create hydraulic cement that could set underwater and gained strength over centuries. But here's where it gets fascinating. MIT researchers discovered in 2023 that Roman concrete's legendary durability arose from what they called hot mixing, adding quicklime at high temperatures, which created self-healing lime clasts within the mixture. When water infiltrated cracks, these particles would dissolve and reprecipitate as calcium carbonate, effectively sealing the damage. Romans didn't understand the chemistry as we do today. They perfected these proportions through empirical observation, creating formulas that specified exact ratios for different structural requirements. Foundation concrete used coarser aggregates and higher lime content. Vault concrete incorporated lighter materials like pumice. This was algorithmic thinking, if-then logic applied to material science. The Pantheon demonstrates Roman computational thinking at its absolute pinnacle. Built around 126 CE, this structure features a 142-foot diameter, unreinforced concrete dome that remains the world's largest of its kind, nearly 2,000 years later. Roman engineers embedded mathematical proportions into every element. The interior height equals the dome's diameter, creating a perfect hemisphere that could contain a sphere of identical dimensions. The dome's 28 coffers reflect sophisticated numerical thinking. 28 qualifies as what ancient mathematicians called a perfect number. Its factors 1, 2, 4, 7, and 14 sum to 28 itself. But these coffers weren't just decorative. They served a computational function, reducing the dome's weight while maintaining structural integrity. Engineers calculated weight reductions systematically, gradually decreasing concrete density from base to apex by incorporating progressively lighter aggregates and increasing void spaces. The oculus at the crown, that dramatic opening to the sky, removed approximately 4,400 tons through calculated design. This weight optimization follows a computational logic that distributes compressive stress optimally, allowing the structure to support itself through pure geometry. They achieved this through scaled models and iterative testing, running simulations in wood and small-scale concrete before committing to the final construction. Now here's a paradox that reveals just how sophisticated Roman computational thinking truly was. Roman numerals, that famous I, V, X, L, C, D, M system, proved remarkably inefficient for complex calculations. You couldn't easily multiply or divide using these symbols. So how did they perform the precise calculations their engineering required? The abacus. Romans relied on this portable calculating device, with beads sliding along wires or in grooves, to perform actual computations. They executed multiplication through repeated addition, division through repetitive subtraction, all on the abacus. Then they translated results back into Roman numerals for recording. Think of them as bilingual engineers, computing visually on one system while documenting in another. Like modern programmers who think algorithmically but write in specific coding languages, Romans recognized that their tool for computing need not use the same notation as their system for recording results. This separation of function from representation demonstrates remarkably abstract computational thinking. The precision Romans achieved through these methods remained unmatched until the modern era. The Pont du Gard aqueduct in France, built in the 1st century CE, maintains alignment accurate to within inches over its 900-foot length. The Colosseum's elliptical plan, measuring 617 feet by 512 feet, demonstrates geometric precision executed without computer-aided design. These tolerances reflect not just skilled craftsmanship, but sophisticated planning algorithms that translated design intent into built reality through empirical iteration, geometric calculation, and systematic observation. These weren't just builders or artisans. They were computational thinkers running sophisticated software in stone and water. Their algorithms, encoded in procedures rather than programming languages, ran successfully for centuries. Many still run today. And they achieved this not through theoretical perfection, but through empirical iteration, testing, observing, adjusting, refining. The lost logic of Roman engineering reveals a profound truth. Computational thinking doesn't require computers. It requires systematic problem solving, iterative refinement, and the wisdom to prioritize practical results over theoretical elegance. Perhaps that's the lesson modern engineers can take from these ancient algorithms, that sometimes the most sophisticated solutions come not from perfect calculations, but from intelligent trial and observation. What do you think? Could modern engineering benefit from Rome's emphasis on empirical testing over pure theory? Share your thoughts and keep exploring the overlooked innovations that shaped our world.